Welcome to the deep dive. Today we're jumping into something fascinating, how AI systems, well, how they actually see the world. Our mission is to get under the hood, understand the mechanics of how AI recognizes faces, objects, scenes. We'll be digging into things like image classification, convolutional neural networks, pattern recognition. It's quite a journey from just pixels to perception.
It really is. And computer vision isn't just lab stuff anymore, is it? It's everywhere. Unlocking your phone, those self-driving car prototypes. So yeah, this deep dive will unpack the core ideas behind it all, drawing on the work of key people in the field. How does the machine do it? That's the question.
Right, so it's everywhere. But the basic question,
Mm-hmm.
how does machine even begin? For us, seeing is just natural.
Mm.
How does AI start? Because an image for an AI, it isn't a picture like we see it. It's just data, right? Numbers.
Exactly. It's basically a huge grid of numbers, pixel values. And this gets turned into what's called a feature vector. Think of it like a long list describing the image in numbers. That's the input.
Okay, a list of numbers. So where does the thinking or the seeing part come in? What were the first steps?
Well, the earliest ideas were things called perceptrons, really inspired by how neurons work in the brain. You've got inputs like dendrites, a processing part like the cell body, and an output like the axon. A perceptron kind of does that, takes numerical inputs, the pixel values, multiplies each one by a weight.
Oh, wait, like how important that pixel is.
Precisely. It simulates connection strength. Then it adds all those weighted inputs up. If the total hits a certain threshold, boom, it fires. Outputs a 1. If not, it outputs a 0. Simple decision.
Okay, so like if you wanted it to recognize, say, a handwritten number 8.
Right. If you had an 18 by 18 grid for that 8 foot, that's 324 pixels. So 324 inputs, each gets its own weight, all feeding into that decision. Is it an 8 foot or not 0?
Wow, 324 little knobs to tune. But how does it learn to tune them? How does it get better at spotting the 8s and ignoring, I don't know, 3s or smudges?
Ugh. That's where supervised learning comes in. It's really fundamental. You need a lot of examples. Thousands of pictures of 8s labeled 8. And thousands of pictures of things that aren't 8s labeled not 8. Humans do the labeling.
So you feed it the answers, basically.
Kind of. You feed it labeled examples, it tries to guess, gets it wrong, and then it adjusts those weights and its threshold bit by bit over many, many examples, trying to minimize the errors. And you always keep some data back, a test set, to check if it's actually learning to generalize, not just memorizing the training pictures.
Got it. Learn from mistakes based on human labels. But I read that the early hopes for these perceptrons were maybe a little ambitious.
Oh, definitely. You hear stories like the U.S. Navy apparently hoping these things would walk, talk, see, reproduce,
Yeah.
become conscious.
Seriously, from a system deciding 1 or 0, that's optimistic.
Highly optimistic. It shows the initial excitement, but that didn't last.
Right, because wasn't there a big critique?
Yeah.
Something that cooled things down.
Yes. From Marvin Minsky and Seymour Papert, they wrote a book pointing out some pretty fundamental limitations of those simple single-layer perceptrons. Their critique, and maybe some skepticism about more complex networks too, really contributed to a slowdown, what people call the first AI winter. Funding dried up, progress stalled for a while.
A reality check.
Mhm.
So the field needed a new approach.
Sort of. It needed different ideas to gain traction. And eventually, this philosophy called connectionism came back strong. It really embraced these brain-inspired architectures, but crucially, focused on learning from data. Lots of data.
And that leads us to the modern era, right? Deep learning.
Exactly. Deep learning and deep neural networks, these are the powerhouses behind the amazing progress we've seen recently. Image recognition, facial recognition, you name it. The deep part refers to having multiple layers of these processing units stacked on top of each other, not just one layer like the early perceptrons.
More layers, more complexity.
Pretty much. And critically, these layers use what are called nonlinear activation functions. That's key. Without them, even a super deep network would basically just be doing a simple linear calculation, like trying to capture a curve using only straight rulers.
Okay. The nonlinearity lets it learn much more complex, wiggly patterns in the data.
You got it. It allows the network to approximate really complex relationships. And the main algorithm used to train these deep networks to adjust all those weights across all those layers based on errors is called backpropagation.
Backpropagation, okay. And for vision specifically, the big breakthrough was convolutional neural networks, or ConNets.
Yes, ConNets. Jan LeCun was a major pioneer here, developed early versions, and worked on backpropagation too. What's really cool about ConNets is how they seem to learn a hierarchy, a bit like what Hubel and Weissel found in studies of the brain's visual cortex decades ago.
A hierarchy. Like learning simple stuff first.
Yeah. The first layers might learn to detect simple edges or corners. The next layers combine those to detect textures or simple shapes. And layers deeper still combine those to recognize parts of objects and eventually whole objects. It builds up complexity.
That makes intuitive sense. Building blocks.
Mhm.
But didn't these convolutions need something else to really take off, like
Yeah.
more data?
Oh, absolutely. That's where ImageNet comes in. This was huge. Fei Li had this vision, you see. She believed the AI needed better data, not just better algorithms.
Yeah.
A massive, diverse data set.
ImageNet, I've heard of that. How big are we talking?
Really big for the time. Over 1.2 million training images, all labeled by humans into 1,000 different categories.
1,000 categories, like types of dogs, cars, furniture.
Exactly. All sorts of things. And getting it labeled was a mammoth task. They actually used Amazon's Mechanical Turk crowdsourcing the labeling work.
Wow. And then they turned it into a competition.
Yep. The ImageNet Large-Scale Visual Recognition Challenge, ILS-VRC, started in 2010. Teams would compete to see whose algorithm could classify the images most accurately. It drove progress like crazy.
So that was the turning point, around 2012.
That was the moment. You had ImageNet providing this massive labeled data set. You had ConvNets, the right kind of algorithm. And crucially, you had the rise of GPUs, graphics processing units.
Graphics cards for AI.
Yeah, turns out they're perfect for the kind of parallel math these deep networks need. So ImageNet plus GPUs plus ConvNets, that combination just blew the doors open for object recognition. Deep learning suddenly dominated.
Okay, so that explains recognizing one main object. But images are often more complex, aren't they? You mentioned multi-label classification earlier.
Right, things have moved beyond just single labels. Now, systems can often identify multiple things in one scene, like see a picture and label it dog, park, frisbee, and person all at once.
That's getting closer to how we see things, but are there still big differences? Limitations?
Oh, definitely. Big ones. One huge issue is the data dependence. Deep learning, as Andrew Ng and Yoshua Bengio point out, is incredibly hungry for labeled data. That's a major limitation for getting to more general AI.
Because labeling everything in the world is impossible.
Pretty much. And this leads to problems like overfitting. Imagine you train a system to recognize cars, but you only show it images of, say, 10 specific models generated synthetically. It might get really good at spotting those 10 cars, but then completely fail when it sees a new car model in the real world. It hasn't learned the general idea of car.
And memorize the training data instead of learning the concept.
Exactly.
Yeah.
And AI can also pick up on weird statistical quirks in the training data that have nothing to do with the actual object. Like, maybe an animal detector learns that animals often appear against blurry backgrounds in its training photos. Then you show it an animal against a sharp background and poof, it fails. It learned the wrong correlation.
That's weirdly fragile.
Yeah.
It doesn't sound like understanding at all.
It isn't, not in the human sense. It's sophisticated pattern matching. And getting these networks to work well, it's tricky.
How so?
Well, optimizing them, tuning all the parameters, Demis Hassabis from DeepMind called it Kabbalistic knowledge, almost an art form.
Network whispering.
Yeah, something like that. He suggested maybe only a few hundred people worldwide are really masters at tuning these things effectively. It's not just standard engineering.
Wow. So it relies on this expert intuition. That seems precarious. And what about deliberate attempts to fool these systems?
Yes. That's another really concerning area, adversarial examples. This is where things get properly spooky. You can make tiny changes to an image, often completely invisible to a human eye, that cause the AI to make catastrophic errors.
Like what kinds of errors?
Think about special eyeglass frames that make facial recognition identify you as someone else, or small stickers on a stop sign that make an autonomous cars system read it as a speed limit sign.
Whoa. That's dangerous.
Extremely. There are even examples where near imperceptible noise added to a medical scan, like an X-ray, flips a diagnosis from no cancer to high confidence of cancer, or vice versa.
That's terrifying. It really shows how different their seeing is from ours.
It absolutely does. It highlights that these systems perceive patterns in ways fundamentally alien to us, and we need incredibly strong safeguards if we're deploying them in critical situations.
So, okay, AI can tell a Dalmatian from a bowl of cherries, which is useful, as Stuart Russell said. But he also said it's a very small part of what real intelligence needs. Fei Li called current AI narrow and task-specific.
Exactly. We've mastered sophisticated pattern recognition on labeled data, but there's a massive gap between that and genuine human understanding. The big missing pieces are things like abstraction, analogy, and common sense.
Abstraction and common sense. How do we even test for that?
Well, one interesting way is using things like Bongard problems. They're visual puzzles, right? You see two sets of simple diagrams, say 6 in each set. You have to figure out the abstract rule that distinguishes the left set from the right set. Humans can often get the hang of it with just those 12 examples, grasping the subtlety of sameness or the underlying concept.
Okay, I think I've seen those. Tricky. How do convents do?
Terribly. Even when trained on tens of thousands of similar same versus different tasks, the best convents performed only slightly better than just random guessing on new Bongard-style problems.
Hmm.
It strongly suggests they just do not have what it takes for that kind of human-like abstract reasoning.
So pattern matching. A plus what? Abstract reason. F. That's a pretty big gap. What's the way forward then? How do we bridge that?
Well, a lot of researchers, including folks like Jan LeCun and Yoshua Bengio, believe a key lies in unsupervised learning or self-supervised learning. The idea is for AI to learn about the world more like babies do, by observing, exploring, predicting without needing every single thing explicitly labeled by a human, building up background knowledge.
Learning the underlying structure of the world on its own.
Kind of, yeah. To develop the common sense foundations. We also see progress with reinforcement learning, like AlphaGo learning, go through self-play. But even RL struggles with transferring knowledge. An agent brilliant at the video game breakout might completely fail if you just shift the paddle up a few pixels. It learned the specific game, not the general concept of paddling a ball.
So it learned the pixels, not the physics or the goal in an abstract way.
Right. Transferring learning to new, slightly different situations is still a major hurdle.
Okay, so wrapping this up, AI vision has come an incredibly long way. It's amazing at specific pattern recognition tasks, changing industries. But that deep, flexible, common sense visual intelligence, that's still a huge mountain to climb. Deep learning is powerful, but as Russell and Orenezioni say, it's just one tool in the toolbox, not the whole answer. It's kind of mind-bending to think about the whole journey, isn't it? From those first simple perceptrons firing ones and nearies to systems sorting through millions of photos, the progress is stunning. But these limitations, the adversarial examples, the lack of common sense, it really makes you appreciate our own vision, our own brains.
It absolutely does. And it leaves us with a pretty profound question, doesn't it? Think about it. Our eyes and brains evolved together over millions of years. The brain provides this incredible context, memory, and reasoning power to interpret the raw data from the eyes. So if our current AI excels at the pattern matching part, but struggles so much with common sense, abstraction, real understanding, what's missing? What kind of fundamental breakthrough do we need for AI to not just see images, but to actually understand the world through them, maybe even in ways that complement how we see it? What really stands out to you listening to this about how AI perceives the world, and what questions does that spark for you about the future?